In the last several years, the lab-on-a-chip community has embraced an exciting technology known as AC electrokinetics. This group of phenomena can be used to manipulate particles and fluids in the micron to nanometer scale in rapid and versatile ways, and is quickly becoming essential for many biochip applications. In this video, we're going to go over the basics of AC electrokinetics in enough detail to help other scientists and engineers who may benefit from using these phenomena in their research. Hi, my name is Robert Hart, and I'm a PhD student here at Drexel in the Department of Biomedical Engineering, Science, and Health Systems. We'll start this video off with a brief description of the physics behind AC electrokinetics. Next, we'll move into device fabrication, and finally, we'll show some videos of AC electrokinetics and explain what's happening.
The first of the three forces we'll be describing is known as dielectrophoresis. Here we see an electric field generated between two submerged electrodes. If we add a dielectric particle into this electric field, it becomes polarized. As you can see, the charges on the particle are balanced by the charges within the liquid. Whether the particle is more polarizable than the liquid or less polarizable can be determined by the Clausius-Moissoti factor. In a uniform electric field, the particles experience no net force. However, in a non-uniform electric field, such as the one shown here, particles that are more polarizable move towards areas of high electric field as they experience positive dielectrophoresis. Changing the frequency to switch the polarizability results in the opposite effect, known as negative dielectrophoresis, and particles move away from areas of high electric field strength. The second force is AC electroosmosis. At the foundation of AC electroosmosis